All right. Um, in this section, we're trying to use all the tools we learned so far, especially derivatives, to do a curve sketching. So let's just work out the example in this section step by step. I'm going to work through it. And this will be a long process. We would like to gather as much as we can information to sketch the graph. So there are 9 steps, basically. Some of the steps are quite straightforward. Some of them are not. So let's just do it one by one. All right. So in the first step, we would like to determine the domain of the function. So this is polynomial. We would like to sketch the graph y equals x cubed minus 6x squared plus 9x plus 2. So that's a polynomial, and we know the domain of a polynomial is all real numbers. In into notation, that will be from negative infinity to positive infinity. So that's easy. And the second step is to find the y-intercept. Okay. All right. So what do we do? We just set x equal to 0 and find the value of the function. So when x equal to 0, y will be what? 0 cubed. Just plug in 0 for x in the function and compute the whole value of the function. Okay. So x cubed minus 6x squared. So that's 0 cubed minus 6 times 0 squared. We know that will give us all zeros, but let's just write down everything in steps. Okay, so in the third step, in the second step, third term is 9 times 6, so 9 times 0. That we know we got all zeros in the first 3 terms, so the answer is 2. So that'll be the y-intercept. So that's how where the curve intersects with the y-axis. And then we would like also to find the x-intercept in this step 2. So we're going to set y equal to 0 and solve for x. Okay, so that's how you find x intercepts. Okay, so what do we get? So we're going to get the x cubed one. Minus 6x squared plus 9x plus 2 equals 0. And this equation is not easy to solve. That's a cubic equation. And obviously, there's no integer solution in here. And it's hard to factor. So we just skip this step. Okay. It's just too complicated. And then the next step is to find the end behavior of the function. So we would like to find the limit of the function on the upper right, to the right and to the left. So, to do that, we can use the limit. We can evaluate the limit of function at the far right. So that means x approaches infinity. So when we do that, okay, so we just oops. Evaluate the limit of the function as x approaches positive infinity. Okay. By the way, I'm using the notation of f(x). That's the same as y. Okay. Just remind you of it. So as you can see, everything as x becomes large and positive, so x cubed becomes large and positive, and the x squared and x. Okay, so we got the large numbers for the first three terms, but the fourth term is just constant. Okay, so we don't have to worry about it. And you can see the first term x cubed. So compared to other two terms, they have small power in x. So that means it will grow much faster than the other two terms. So at the end, the behavior of the function is dominated by the first term, and that will give us positive infinity. Okay, as we know, x cubed approaches infinity as x approaches infinity, and similarly, we can find the limit of the function as x approaches negative infinity. Okay, and we use the same argument as you know, the first three terms, gets large in magnitude, so they have some difference in the signs, but the magnitude of all the three terms, the first three terms, get large, and the fourth term is just constant. We don't worry about it. But again, because the first term is x cubed, the highest power, so it will change much faster than the other terms. So again, this will be dominated by the first term. So x cubed as x approaches infinity, the magnitude gets large infinity, but the sign will be negative because it's cubed. So if you cube a negative number, you get a negative number. So the limit of this function as x approaches infinity is just a negative infinity. All right, so that means, oops. So from here we can see that, on the right, on the far right, that the curve keeps going up without bound, and on the far left, the curve keeps going down without bound. Okay, so the next step is to find asymptotes of the curve of the graph. Well, we have different types of asymptotes. We have horizontal asymptotes, we have vertical asymptotes, and oblique or slant asymptotes. All of those asymptotes appear in rational functions. In polynomials, there will be no asymptotes. So this one, we don't have to worry about that at all. Okay. So no asymptote. All right. Okay. Increasing and decreasing of f. So this time we have quite a few things to do. So we're going to use the first derivative. Okay. We know that when the first derivative is positive, the function is increasing, the first derivative. When the first derivative of the function is negative, then the function is decreasing. All right. So now we need to find the derivative of the function. Okay. I guess I'm going to write down the function here. So let's just do it step by step. So y equals x cubed minus 6x squared plus 9x plus 2. You can use f or y. So why don't we just use y here? Okay. So we can find the derivative of the function. So that's y prime. And we know how to do that. Just do this step by step. So x cubed, we got 3 times x squared. If we use the power rule. Okay. 3 to the front, and the 3 minus 1 is 2. So that's the exponent. And then we got 6 times minus 6 times the derivative of x squared is just 2x. You know, again, the power rule, you know, put 2 in the front and subtract 1 from the exponent. 2 minus 1 is just 1. So that's x of 1 or x. And then plus 9 times derivative of x, but the derivative of x is just 1. Okay. So that's that. And then at the end, we got the derivative of 2, which is 0. So at the end, the derivative is just 3x squared minus x plus 9. Okay, so I'm going to factor it out, and you know, we're going to find the critical numbers as we did before. So this involves quite a bit of work. So first, let's just factor out 3 from all the terms. So then it becomes x squared minus 4x plus 3. If you factor out 3 from all the terms, that's what you get inside. So there's 3 times this trinomial that can be further factored out into x minus 1 and x minus 3 if you do it. Okay, so that's x minus 1, x minus 3. Okay. So you just find the two numbers. When you multiply them, -1 times -3, you get +3. Okay. And when you add them, you get -1 plus -3, so that's -4. So that's right. And then you set y prime equal to 0 to find the critical numbers. Okay, so let's just set y prime equal to 0. And then that will give us the critical numbers. Okay, so then we got two equations. X minus 1 equal to 0. We just set each factor equal to 0. Or x minus 3 equal to 0. Okay. So then we get another critical numbers. Okay, so if you solve these two equations, the solutions will be x equal to 1 and x equal to 3. So x equal to 1 and I just write this. Those two solutions same, you know, together. So these are the two critical numbers. Then use the two critical numbers numbers 1, 3. Three subintervals. Okay. So what are the subintervals? The three subintervals. You know, negative infinity to 1. Okay, so we got three subintervals. Okay, so the first subinterval would be negative infinity to 1. So we know the domain of the function is from negative infinity to positive infinity, as we know. So then these two critical numbers will divide the whole domain into three subintervals. The first subinterval from negative infinity to 1, and the second subinterval from 1 to 3, and the third subinterval from 3 to infinity. Okay. Oh, wait. And then inside each subinterval, you know, the function is either increasing or decreasing. It will not change the behavior. So let's just pick up a test value of x in each subinterval and see whether the derivative is positive or negative. Then we can determine whether the function itself is increasing or decreasing. Okay. So in the subinterval from -1 infinity to 1, so we can pick x equals 0. So that's a good number, easy to compute. So, so then you just you know, plug into the derivative of the function. So y prime is equal to 3 times. Okay, that's the y prime. Okay, we already did that. So so plug in 0 for x. 0, 0. Okay, see what we get. So we got 3 times -1, 0, 0 minus 1, -1, 0 minus 3 is -3. So this -1 and -3 is multiplied, we get +3, and multiply 3 in the front, we get the +9. So that's positive. So the first derivative is positive, thus the function increases. Okay, so that's the first subinterval. So then the same thing for the second subinterval, from 1 to 3. And once again, we just pick up a test value. This time we're going to pick x equal 2. So 2 is between 3. And then we just do the y prime again. Okay, let's see. Y prime is 3 times 2 minus 1 times 2 minus 3 again. You know, we just plug in 2 for x. So 2 minus 1 is +1, 2 minus 3 is -1. So we got 3 times +1 times -1. So that's -3 if we do it. So it's negative. So the function is decreasing. So that's the second subinterval. Now we have to do the third subinterval from 3 to infinity. So again, just pick up the number x between 3 and infinity. So this time we can pick up 4, for example. Then just to calculate y prime and see what happens. So just plug in 4 for x instead of 2. So we get 3 times 4 minus 1 times 4 minus 3. So 4 minus 1 is 3 and 4 minus 3 is 1. So we get 3 times 3 times 1. So that's positive 9. So it's positive. Okay, so again, the first derivative is positive. That's the function. So we can use the information, in step 5 to locate the extreme of the function. Okay, so just okay, enlarge. Okay, so we can either use the first derivative test or second derivative test. It turns out it's a little easier to use second derivative test. So why don't we just do the second derivative test to locate the derivative extrema of the function, remember? Okay, so to do that, we need to find the second derivative, first. So we know the first derivative function is 3x squared minus 12x plus 9. So if you take the derivative of that, you get second derivative. So the first term, x squared, take the derivative of x squared, 2x. So that will be 3 times 2x. And the second term is negative 12 times derivative, times derivative of x. So the derivative of x is just a 1. So times 1. And the derivative of 9 is 0. So we get this plus 0. So 3 times 3x is just 9x. And 12 times 1 is just 12 now. Then we can test the sign of the second derivative of the second derivative. We can test the sign of second derivative at each critical number and see this, what happens. So at the first critical number, x equal to 1, so you just plug in 1 for x and see what it get for the okay, anyway. So the second derivative of the function is 9x minus 12. So if x equal to 1, then you just plug in 1 for x. So that's 9 times 1 minus 12. So when x equal to 1. So that's 9 minus 12. So that's negative 3, isn't it? So that's negative. So we know at a critical number when the second derivative function is negative, the function is a relative maximum. Okay. So next, we do the same thing. X equal to 3. Okay. So at x equal to 3, so we got well, double prime equals 9 times 3 minus 12. So that's 27 minus 12. So that's 15. So that's positive. I hope I did everything right. Oh, okay. I'm sorry. This 3 times 2x, not 12x. 2. So that's 2x. I'm sorry. It's the second derivative is 3 times derivative of x squared. So 3 times 2x, not 3 times 3x. So, so that's 6x. 3 times 2x is 6 minus 12. So that's 6 in here, 6 in here. Okay. So we get -6. So the number is different, but it does not change the sign, unfortunately. So it doesn't change the conclusion. So then, you know, when x equal to 1, we get the negative number. So for this second derivative, so the function has a relative maximum at x equal to 1. And at x equal to 3, the second derivative of the function is 6 times 3 is just 18. 18 minus 2 is positive 6. So that's positive. So the function has relative minimum. As you know, when the second derivative is positive at the critical number, the function attains relative minimum. Okay, so that's minimum and maximum. Okay, so that's step 5 and step 6, pretty long. So the next thing is the concavity of f. So this time we're going to use the second derivative. Okay, so what do we do? We're going to set the second derivative function to 0 and then solve for it. So we're going to do it. Then we can find the critical numbers. So if you set the second derivative of the function equal to 0, so then we get 6x minus 12 equal to 0. We already did the second derivative of the function here. So that's so that's 6x minus 12 equal to 0. So so you can easily solve the equation to get the what x equal to. Okay, so you can move x to the right hand side, or 12 to the x to the right hand side. So we get 6x equal to 12, and then you divide by 6 on both sides. Okay. So then so what is the critical number? X equal to 2. So that's the inflection point. Okay. And then once we get that, then we can split the whole domain or divide domain function using the inflection point. Inflection point x equal to 2. So So then we get two subintervals. And divide the domain function into two subintervals. Okay, so these two subintervals are from negative infinity to 2 and 2 to positive infinity. Okay, negative infinity to 2 and from 2 to infinity. We only get one inflection point, so so it just splits the whole domain into two subintervals. And then we just test the sign of second derivative in each subinterval. So let's just do that in the subinterval from negative infinity to 2. We can pick up x equal to 1, for example. Okay, so 1 is less than 2. So then y double prime will be what? Uh, 6 times x. So that's 6 times 1. If you plug in 1 for x, that's what we pick. It's 12. Okay, 6 minus 12. 6 minus 12. So that's 6 minus 12. So that's negative 6. So negative. So we know when the second derivative of the function is negative, the function is down. Okay, and then we can do the same thing for the other subinterval from 2 to infinity. All right, so this time we can pick up x equal to 3, for example. Okay, so let's just do that. So 3 is greater than 2. So we get y double prime, the second derivative function equals 6 times x. So that's 6 times 3. So that's 18. 18 minus 12. So that's 6. So it's positive. So that means the function concaves up. So that's what we can, do for the second derivative and what second derivative tells us. So step 8, we have inflection points, just one inflection point, x equal to 2. We already found in the step 7. Okay, so there's one inflection point. Okay, in the last step, we need to pick up some other values of x and sketch the graph. So we got all the information, but that will not be good enough. So we might need some extra information to draw the sketched graph. So let's just pick x equal to 4, for example. Let's just pick another number and try to draw some more points. So x equal to 4, that gives us another point on the graph. So x equal to 4. So then So y equal to this. So plug in to the function y. So that's x cubed. So that's 4 cubed times 6 times 4 squared. Okay, so we need to put the parentheses in here. So that's 6 times 4 squared x squared. So that's 4 squared. And then we get 9 times x. So that'll be 9 times 4. Okay, so plus 2. So let's see what we get. So 4 cubed, that's 64. Minus 6 times 4 squared is 16. So we get that. 16. Okay. Plus 9 times 4. So that's plus 36. So let's see. So this 64 minus 6 times 16, that's 96. Plus 36. So what do we get? So 64 minus 96, so that's negative 32 plus 36, that's positive 4. 4 plus 2, that's positive 6. So then we get another point. You know, we get another point on the graph. And the point is 4, 6, right? The point of 4 is on the. So that's just some extra points we need to draw the graph of the function. And at the end, we can draw the whole, sketch the graph of the whole function using all the information here. So let me just give you the final graph in here as we did it before. So this is the graph of the function, okay? So, we have the domain is all your numbers. Okay, so the curve extends from the far left to the far right. The y-intercept is 2, so it's in here 2, 1, 2. And we didn't do the x-intercepts. There's no x and y-intercepts. The limit of function as x approach past infinity, f approaches past infinity. As x approaches negative infinity, f approaches negative infinity. So the curve goes up on the far right, and it goes down on the far left. Okay, goes down on the far left, it goes up on the far right. Okay, and then there's no asymptotes. Okay, and then increasing and decreasing from negative infinity to 1, the function is going up, increases. From 1 to 3, 1 to 3, 1 to 3, the curve goes down. From 3 to infinity, the curve goes up. Okay. And relative extrema at x equal to 1, we got relative maximum. At x equal to 3, we got the relative minimum. Okay. Concavity from negative infinity to 2, negative infinity to 2, the curve concaves down. From 2 to infinity, the curve 2 to infinity. So that's 2 to infinity, the curve concaves up. Okay, so change the concavities, and the inflection point is at the x equal to 2 in here. Okay. And the other point that we just picked up is 4, 6, 4, 6, right? 1, 2, 3, 4, 6. Okay, so 4, 6. So that's the only point that we needed. So if you just connect those points by a smooth curve, that will give us, you know, the graph. All right.